I know. I want to do it.
Like what do you want?
I'd rather use the AP, but you can't just go straight to the AP.
Yeah, not like this touch. Although, no, sorry, not like physics, actually.
Yeah. Which I'd probably be doing for you.
Hello,
Hey,
welcome back to school. Good to see you guys. Hope you're doing well. Hope you, obviously it's sad that break's over now, but I hope you at least can reflect on break and hopefully you got some sleep in, some relaxing time, some family time, and maybe you're a tiny bit refreshed, baby bit refreshed. Maybe all the refreshment's gone and you're sad now because it's school again. I don't know. Either way, too bad, so sad. Here we are. What I'd like to do is start with acid-base stuff. We finished 4.8 before you guys left. Or, well, you guys were already gone, I suppose, but before the A folks left, no, B folks. You guys are A folks. Gosh, I hate this. Never remember who's who and which group is which.
Yeah, this is good. All schools instantly pass me.
Good luck. Good luck with that. But this is 4.8 stuff. I'd like to refresh it because it's been, 13 days since anyone maybe even remotely looked at this. So let's start here. I have 3 problems asking for net ionic equations. I'd like you to see if you can write these up. Be aware, the key point here is strong versus weak, right? If it's a strong acid or base, what do you do? Dissociate. If it's a weak acid or base, keep it together. That's all I'll say. Give these 3 a shot on a separate piece of paper on the back of a note sheet. If there's a blank side of a note sheet, you can do it there, that's fine. But somewhere on some piece of paper, give these a shot. Let's revisit some old stuff for just a second, then we'll jump into some new stuff eventually. But I'd like to see what you guys can remember after weeks of not chemistry. Oh, they're skipping everything. Come here. No, his mother. His mom is my son's teacher right now.
First grade?
Yep.
Yeah. First grade.
First grade, yeah.
Yep. His mom teaches my son.
This is Deeks.
My brother has me.
Really?
I think so. I can send him my grade.
Is he first grade?
Good second grade.
I was the only kid who had to read, and everybody else had to have math. I was so mad.
Wait, why?
That's the plight of being smart.
Because nobody else can read.
It's why
There's
first
a-
grade.
Just randomly kind of figuring on that. Like, there's a big philosophical issue in education with what to do with the smart kids.
Oh, yeah, especially elementary.
Yes,
It's such a mess.
Because so much of it feels like you're just giving them extra work, which just kicks them off.
What it is.
You know what I mean? Like that. Like that's exactly what that is. Is like, hey, you're really smart and you can read better than all your peers. Here's more reading while they get to sleep. You're like, no, dang it, I want to sleep. I don't know. So like I feel like differentiating for elementary kids where it's like some kids need, they're remedial, they have a lot of help.
Yeah.
There's a whole middle group, and then there's the high group where it's like, oh, you're done after 4 minutes when everyone else needs a half an hour. Here's my stuff.
When I was in elementary school, still in Oklahoma, I was at this private Christian school.
Okay.
And so I would finish all my work way ahead of everybody, and I would be disruptive of the classroom because I was talking to my friends.
Speaking of which, how are these problems?
They're going great.
Great.
Yeah,
Okay,
yeah,
so everyone stop.
This is a good story.
I'll let you finish it after you finish the first round.
Problem.
Don't mind the word solution, by the way. I should have. They're all solutions. They're all aqueous. Okay, sorry. That feels like it might be confusing because it's there and not in the other two. Don't overthink that.
Well, I jotted down notes for everything I didn't know.
All right. When you are all done, I have one more question. For number 1 and number 3, identify conjugate acid-base pairs. That means. What's perchloric acid? That's on your list. Find perchloric and just switch the chlorine with the bromine. Yeah, a little curveball. So miserable. Perchloric acid is a strong acid. Once you finish the net ionics, again, for number 1 and number 3, if you could identify the conjugate acid-base pairs for number 1 and number 3. Just again, trying to refresh some old stuff. How are we doing? Questions? For those of you at home, if you didn't hear, bromic acid has the same formula as perchloric acid, just switching out the chlorine with bromine. Right? All right, so let's get started. Nitric acid. What's the formula for that? Strong or weak? Strong. So therefore, I should write it dissociated. Ammonia. Formula. Strong or weak? Weak. Okay. Now, this isn't net ionic yet. I'm going to cross things off, right, once I hit my product. So I have a nitrogenous base, as it's called. Okay? A base that contains nitrogen. When we have these are Bronsted-Lowry acid-base reactions. They are bases. They accept a hydrogen from the acid. Here's my acid. It'll donate its hydrogen over here. And on the product side, we are left with the nitrate and ammonium. Okay? Spectators? Nitrate. Nitrate did a whole lot of nothing. So the net ionic should be H1 plus ammonia yields ammonium. Okay? So far, so good? Again, it's the strong versus weak thing, right? You can identify which acids or bases are strong, they break apart, they're dissociated. With the weak ones, stay together. They're written just as the formula says. Hydrofluoric acid, what's the formula? HF, strong or weak? It's weak. Somebody said strong, right? Okay. It's fine. It's weak. Now, this is the one that's tricky. This is the one that feels like it wants to be strong because all of its neighbors are strong. HCl, strong acid. HBr, strong acid. HI, strong acid. But HF, hydrofluoric acid, is weak. Okay, so it stays together. Rubidium hydroxide. Formula? Rubidium just a 1+, right? Strong or weak? Strange. Strong or weak? How do you know? Yeah. So when your cation, right, comes from one of the first two columns with hydroxide, so whatever from the first two columns, hydroxide, they're all strong with one exception, but that's an exception I'll never give you. That's beryllium. I won't give you that example. It's just annoying. Okay. So we have a strong base. So what do? We dissociate it. Weak acid, strong base. This is an Arrhenius version of acid-base chemistry, right? Now we're going to have the H and OH come together to produce water and salt. The salts that we get from acid-base reactions are always aqueous, every single time. Okay, we make water, we make salt. That salt is aqueous salt. Salts are strong electrolytes, meaning they dissociate. When they dissolve in water or when they're aqueous, they are broken apart. So I'm going to end up with rubidium chloride, but it's not going to be together. It's going to be separate like such. Let's see if I can do this. There we go. Okay. Spectators. Rubidium didn't do a darn thing. There it is. There it is. It's gone. So our net ionic ends up being HF plus hydroxide yields water and fluoride ions. Third one, for bromic acid, you looked it up. What'd you find for the formula? Okay. Strong or weak? Weak. Now, same exact structure as the perchlorate, but it's not one of our 6, is it? If it's not one of our 6 on that list, it's weak. Weak together. The other part of this is methylamine. I gave you that formula. This is a nitrogenous base, one of the bases that contains nitrogen. They are all weak. So weak. We mix them together. This is Bronsted-Lowry. Every single time you have one of these nitrogenous bases, you're just going to transfer a single hydrogen, a single proton, and that's the reaction. Here's the acid, it'll donate. Here's the base, it'll accept. And on the product side, we get perbromate, which is a polyatomic ion, plus the cation version of methylamine. Okay? Spectators? Nothing. Everything changed. Something happened to all of our species, right? All of our chemicals. Yeah.
How did you know that the H would get donated to the H2?
Oh, okay. Good question. Whenever nitrogenous bases, ammonia, methylamine, or other things that look like this, whenever they accept the hydrogen, the extra hydrogen always goes on the nitrogen. Every single time. Okay? Now, the reason why that is has to do with charges. The hydrogen is positively charged. In this molecule, that nitrogen is very negatively charged. Has a nice big partial negative charge on it. So that hydrogen is more attracted to the partial negative of the nitrogen. And that extra one will always get put on the end. Make sense? Okay, so no spectators, that just is what it is. Let's do the last part here. The last part I'm asking you to do is identify the conjugate acid-base pairs in reaction 1 and reaction 3. Let's go back to reaction 1. What's the acid? This thing's the acid, right? Now, it's dissociated, but that's still my acid, right? So really, I'm going to write A right there, because it's that whole thing. That thing is my acid. This is the base. On the product side, we cross off nitrate, okay? But the nitrate is my conjugate base. Remember, when it comes to acid-base pairs, conjugate acids and conjugate bases, or I should say, an acid and its conjugate base are different by one hydrogen, right? So here was the acid with a hydrogen. Here's its conjugate base without a hydrogen. Here is the base. Here is its conjugate acid after it's gained a hydrogen. Okay? Now, again, when you identify these, in terms of acid and base, hopefully it's not too bad. Your acid will generally have a hydrogen as the first element in that formula. Your base sometimes has hydroxide, sometimes doesn't. If it doesn't have hydroxide, it's going to be one of these nitrogenous bases. Okay? And then its conjugate pair is just different by a hydrogen. After an acid has donated its hydrogen, you end up with a conjugate base. After a base has accepted a hydrogen, you get a conjugate acid. Ring a bell? Sound familiar? Cool. Third one. Acid base. Which one's the acid? Which one's the base? Yeah, the one that's called acid is acid. It all adds up. It all makes sense. That's my acid. Hydrogen's written out front, kind of dead giveaway. Here's my base. It's got the nitrogen group at the end there, NH2. This donates, this accepts. After the donation has finished, acid turns into conjugate base. And base, after it's accepted that hydrogen, turns into conjugate acid. Okay? And then if I wanted to, I could bracket these, right? I didn't do it for the first one. I didn't have room. That's a pair. That's a pair. Okay? Old news? Cool. Let's try some more old stuff. This is the very last thing we did before we ran away. You were at home. This is a hard concept, I think. I'd strongly recommend you go back to the very bottom of 4.8 and try to refresh your brain real quick. See what you can do on these three salts. I'm asking you to figure out whether these salts are acidic, basic, or neutral. Okay? They are all salt. I didn't give you a weird one that's not a salt. These are all salt compounds. They're all ionic. My question to you is, can you figure out whether these three salts are acidic, basic, or neutral from not last week, I suppose, 2 weeks ago, from the notes from 2 weeks ago, Tuesday, before we left for break. I'll give you a chunk of time to contemplate life, and I'll jump in and help you out. How's this treating you? That's about as optimistic as I could be, I think. Meh. Okay. Let's use these three and try to revisit 2 weeks ago. Okay. When it comes to figuring out whether a salt is acidic, basic, or neutral, you have to analyze the two parts. Okay. We have a cation and we have an anion of our salt. The cation of your salt generally comes from a base from an acid-base reaction. Right? The anion of your salt comes from the acid. So if we can figure out which acid and which base the ions came from, we can then analyze whether the salt overall should be acidic or basic. Okay, here's the problem with this. And if you're on 4.8, you can look at that, like, I had a little chart, right? And there was two arrows, and they went like that. One was pointing up, one was pointing down, and on one side it was the acid, the other side it was the bases. Okay? When you have conjugate acid-base pairs, if the acid is strong, the conjugate base is on the complete opposite side of the spectrum, meaning strong acid, neutral conjugate base. There's three levels of like acid or base strength. There's strong, there's neutral on the opposite extreme, and then the whole middle ground we call weak. Okay, I warned you about this before we left. I'll say it right now again because it's been 2 weeks. Strong and weak in chemistry are not opposite. Okay, that's really, really, really annoying. But strong acids and weak acids are not opposites of one another. Okay, a strong acid is one extreme of that scale. The other extreme is called a neutral substance. Okay, something that's literally a worse acid than water is. Water is a stronger acid than a neutral substance. Okay, it's weird if that sounds. So if I have a strong acid, its conjugate base is neutral. If I have a strong base, its conjugate acid is neutral. If I have a weak acid, that's somewhere in the middle, its conjugate base is also weak, somewhere in the middle. Okay, so let's think about this for a second. Potassium iodide. Okay, the two chunks. I have potassium, I have iodide. Okay, what base would this have come from? Potassium hydroxide, KOH. Is KOH strong or weak? This is a strong, or sorry, this came from a strong base, right? Now, this ion is the conjugate acid of that strong base. If this came from a strong base, this ion itself must be neutral. Okay? The base it came from was strong, the ion in the salt is neutral. This one, what acid did that ion come from? Hydroiodic acid, strong or weak? Strong. Hydroiodic acid is strong, therefore the iodide ion in the salt is neutral. Neutral cation, neutral anion, overall this salt is neutral. Okay? Number two, lithium chlorate, not perchlorate, but chlorate. Let's break it in half. Lithium, what base would this have come from? Lithium hydroxide, strong or weak? Strong. Therefore, the lithium ion, as its conjugate, is neutral. Okay, ions that come from strong acids and strong bases are neutral. They don't affect the pH at all. Chlorate. Okay, this would have come from this acid. That's called chloric acid. Strong or weak? It's a weak acid. It's not one of our six, right? Perchloric is, hydrochloric is, but chloric acid is not. So this is a weak acid. That ion in our salt is the conjugate base of that weak acid. If this is weak, what does that tell me about that? It's also weak. Now, that sounds so weird to say in your head, right? Like that feels like it's the wrong answer, but weak is the middle ground. So when something's strong, its conjugate is neutral. If something's strong, its conjugate is neutral. But if something's weak, it's in the middle, and therefore its conjugate is also in the middle. And that means it does have properties of either acidic or basic, depending upon where it came from. So now we've got to think. This is the ion. It came from an acid. Therefore, this is basic, a conjugate base. Yes. And it's a weak conjugate base. It means it messes with the pH a little bit. So this was a neutral cation and a basic anion. Overall, this salt is it's basic. You're basic. Anyway, this one, this gigantic cation out front, that came from a nitrogenous base, right? This half is CH3, NH3, 1 plus. You can think of it like it's ammonia, right? Ammonia, NH3 is a base. Ammonium, NH4 is a conjugate acid. So this is the conjugate acid of CH3, NH2. Nitrogenous bases, strong or weak? They're weak. Ammonia and any of those other nitrogen bases that show up, they're all weak. Therefore, this as its cation, as its conjugate acid is also weak, because weak's the middle ground. Good job. So therefore, this is an acidic cation. On the other side, we have bromide. What acid did that come from? Hydrobromic, strong or weak? Okay, so bromide is neutral. Yeah, right? Okay, so this came from a strong acid, therefore that ion is neutral. This came from a weak base, therefore that cation is weak. Meaning, this is going to mess with the pH. That is neutral, it will not. This is a conjugate acid, therefore it's acidic. And overall, I have an acidic salt. Okay? I have more of those for you to look at on the review sheets. So let me I'm going to transition here to 4.9. We're on the last topic, 4.9. We're going to start it today for the last 20 minutes or so. Okay? It's on redox. It's going to take probably 2.5-ish days, give or take. We might finish on Wednesday before the end of the hour. Hopefully you. We'll see. And once we're done with 4.9, that's Unit 4. My anticipation is that we have a test on next week, Monday. Meaning, if we have a tail end of Wednesday left over, we'll start reviewing. Thursday will be an in-class review this week. Friday, I'm going to be probably pretty nice to you if I had to guess, because I think we've stacked a couple of labs that not everyone has completed. So if you're a person that left a couple labs hanging out there before winter break in December, I'll leave Friday to kind of maybe hopefully catch somebody up. Sounds good in theory anyway in my teacher head. But I probably won't give you a ton on Friday, if anything, on Friday this week, okay? Because we'll have a test on Monday next week. So you can use Friday, again, in my teacher head, this sounds good. In theory, you can use Friday to maybe look at some things and ask me questions if I'm hanging out in the office. That sounds good. Anyway, so that's a little review on acid base, and by little, I mean it took us a half hour. That's okay. I kind of wanted it to take a half hour, but I think that helped. But let's start doing some redox. I'm sorry, Jagger, did you want to tell your story about Oklahoma and children in elementary school?
Oh yeah, so I'll keep it short. So I would finish all my work early, and I would be disruptive of the class because I was talking to my friends. So the way this school was set up is every class was in a different building, and so they made me go down to the principal's office to wait until the next period, which was the next class. So they sent me there just to wait it out, like color, do something stupid like that. And principal thought I was in there for being a bad kid. It being an Oklahoma private Christian school, they punished me as accordingly. So they took their big yard-long paddle and they made me put my hands on the desk and spank me. And then that was how I became introverted, like the rest of my school career until this year.
Oh, I was gonna say that's flip though, right?
No, yeah, it was like it went like a parabola. It went like
Your math teacher could be proud.
Yeah. And then they said, oh, pray, he turns out all right. And then I just said, yeah.
Yeah.
I'm gonna leave it there. Don't worry, I would never smack you with a paddle. Okay, good one. All right, so let's do redox. Now, you did this last year, I think. Don't worry.
Yes.
We did. This was during quarantine though.
Yeah, so we're gonna start at phase one. Okay, we're gonna start over. I'm sure I'm gonna go faster than was taught last year, but I'm gonna start at literally the very first step of redox, because it's a multi-step kind of thinky, problem solve type of problem. I genuinely enjoy these. I think these are some of the funnest problems that we do in terms of like problem solving. I really like them, and that is not sarcasm. Maybe you're not surprised, but I don't know. I like they're fun. So we're gonna get started with a review. Oil rig stands for what? Uh-huh.
Ionization.
Loss.
Oxidation is losing, or yeah, we'll go like this. How about that? Losing maybe electrons. Okay. Rig reduction is can't spell. Gaining electrons. Okay. It's really important that you know that. A redox reaction is when electrons transfer. One substance moves electrons to the other substance. Okay. Redox is the most common type of chemical reaction that exists. Redox reactions are pretty much the vast majority of all chemical reactions you encounter in real life. Okay. Very, 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 very common type of chemical reaction. So here's a little chart, same exact stuff. Oxidation, gain or loss. Is the oxidation state or oxidation number going up or down? Hold on. Don't answer that. Reduction. Gain. Okay. This is named off of how the oxidation state changes. Reduction is called reduction because the oxidation state is going down. Okay, that's literally where that name comes from. And then in turn, oxidation must be
Up.
Yeah, the opposite. Thank you. Yes. Okay. Where are the electrons in the half reaction? I don't know if you've done that in a while. Maybe you have. Remember what a half reaction is? Here, hold on. Ooh. Remember those boxes?
Yeah.
You just take like half the stuff.
Yeah, you can take like Al, just Al.
So when we balance redox, you take half of it and the other half of it and you balance them separately and then bring them back together. In the half reactions, we have electrons. In one of these, the electrons show up on the reactant side. In the other one, the electrons show up on the product side. So that when we combine them, the electrons are canceled out basically, or it's however many we've lost, we've gained. Does that make sense? So let's think about that. Let me go back to where it was. Where are the electrons in the half reaction? On the product side or the reactant side? Okay. If it's oxidation, we're losing electrons. Where would the lost electrons show up? On the reactant side or the product side? That was perfectly split. If the electrons are lost, do they show up on the reactant side or the product side?
I thought it'd be the product, because if you start out and you lose them, they went that low over the product.
That's what I would say.
It's that one. Okay, so yes, when electrons are lost, they show up on the product side. The original reactant had those electrons, and then after the reaction has occurred, the electrons are separate or gone or removed from whatever that substance was. So for oxidation, these are on the product side. And for reduction, the opposite, right? They're on the reactant side. Okay. We'll see that, obviously, as we try one of these. I don't think we'll even try one. Because before we can do any balancing, we need to make sure we can do oxidation. Yes, Jake?
You said the test is next week?
Next week, Monday.
I thought you said there wouldn't be a test for the rest of the semester.
I said there wouldn't be a test of warming grade.
Oh, okay. I guess you didn't read the script.
Read what script?
The script, we all got a script, and it said that you wouldn't give a test for the rest of the semester. We all thought that.
Actually?
Yeah, that's what we all thought. I was all happy with stuff, like, no final, I don't have to take another test for chem, and as long as I do lab and homework, I'll be fine.
The Unit 4 test should be pretty darn easy.
It doesn't make it, like, it's the principle.
It's like a one question test.
This,
What color is this?
please don't like, not take my test seriously next week. But I honestly think Unit 4 is the easiest of all the things to talk
I
about.
would hope so. This is mainly review.
Yeah, well, and that's why I don't like saying that necessarily, because there are people that will struggle with next week's test. And maybe they even try and they prepare and they study and they still might struggle a smidge with next week's test. So for some people, it's not the easiest test. But I think like this is the most reviewy of anything that we do all year. Because after this point, there is zero review. Like Unit 5 forward is all new stuff. Sorry, not true. Unit 7 for you.
Are there 7 units?
There's 9 units.
There's 9. Are we going to cover all 9?
Yeah, we're gonna get there.
For the AP?
We'll get there. Yeah, we got 4 months. We'll get there. About a unit a month, a little under. Unit kinetics. Which means nothing to any of you because you've never learned chemical kinetics before. Related. Yeah, kind of. It's the rate of chemical reactions.
Oh, so it's like the speed on how fast.
Yes. It's unique. We'll deal with that in a week and a half. Or a week. Well, next week Tuesday I'll be teaching that stuff. Fun. All right, anyway. So you got some rules. That whole front page for 4.9 is basically just review stuff and rules for us to use later. What we're going to do today is we're going to practice assigning oxidation numbers. Okay? In order to balance a redox reaction, we have to have the correct oxidation numbers for every single element. If you can't get the oxidation numbers right, you're going to have no chance at balancing. Just the truth. Okay? So we've got to start here, and we've got to make sure we can do this before we even remotely try to balance a redox reaction. Because if you get the numbers wrong, you're done. You're not going to get it right. It's just not possible. You need the right numbers from the starting point in order to balance this correctly. So here's the rules. I think we used this once last week or 2 weeks ago, or not last week, obviously. 2 weeks ago, I think, when we did 4.7, which was types of chemical reactions. I very briefly reviewed oxidation numbers, and it was the same rule that I had on that sheet that I have on this sheet. But we'll practice that in just a second. Okay, a little more review. Redox reactions are reversible. An oxidation half reaction, if I run it in reverse, is called. If I run an oxidation half reaction backwards, it should be called reduction. The opposite of oxidation. Oxidation and reduction are opposites, right? So if I run it this way, it's oxidation, but I can flip the whole darn thing and run it that way to make it reduction. Okay?
So like you can do with the products and reactants?
Yep.
Okay.
Now that sounds weird because generally chemical reactions only go in one direction. Okay. So in order to actually do this in a lab setting, you have to mess with the conditions pretty substantially to make it go the wrong way.
Can you reverse a lot of chemical reactions?
A good chunk of them, yes. But again, it usually requires some pretty heavy manipulation. For example, like their electrolysis is a type of chemical reaction where you literally use electricity to force a chemical reaction to go backwards the way it wants to go. For example, your phone. the battery in your phone. When you charge your phone and you plug it in, okay, you're pumping electricity into the battery to run redox backwards so that it charges up the battery. Then when you use your phone normal, it runs redox the way it wants to run redox and supplies electrical energy to your phone. Good question. It's generally not great for your battery because it's trying to do both things at once. But batteries have gotten pretty darn good where it's able to do that. I mean, it's constantly just flip-flopping back and forth between, I'm sure it's a mess. I can't imagine like on a microscopic or atomic level what's happening. It's probably just pure chaos. Because you're running the same reaction, but it's fighting each other and trying to do both at the same time as you try to use your phone and charge your battery. Yeah, it's probably not, I don't know.
So on battery, and you know when it like heats up, if you like a D-cell battery and you disconnect both of them, what happens?
So you're saying like you're connecting the terminals?
Yeah, like you know when it gets like really hot.
Can't say I've done that.
Well, yeah, that's what I'm saying. Like, why is it not safe? Why is this like overheat and break?
So you're completing the circuit, so to speak, in that situation. It's just that your electricity's got nowhere to go.
Well, it's like it's charging and taking out of the.
Yeah. Well, and even when you charge your phone, if you use your phone while you're charging, it generally gets pretty darn hot too. We'll talk more about this stuff once we get to thermodynamics. That is number 6 and number no. Yeah, number 6 and number 9. Yeah, 2 units on thermodynamics. Because there's kind of a conceptual chunk of it, and then there's the math chunk of it.
Why?
Conceptual. Then the math gets a little funky. All right, so this is the next chunk of your sheet, and this is how to balance things. But again, you can't balance things without oxidation numbers, so we'll just ignore this for right now. We'll come back. Work. Ooh, I don't think we'll do this at all. When you balanced redox reactions last year, everything you balanced was under acidic conditions. You can actually balance redox under basic conditions too. It adds just a couple rules at the end here to change it from acid to base. AP doesn't really test on this. Maybe we'll do it if I'm feeling extra fun this week, but we might not. Because really, most redox is under acidic conditions anyway. All right, so here's what I want to do in the next 8 minutes. I want to get started. You have a giant page. And on this giant page, there's a bunch of blanks. What we need to do is assign oxidation numbers for every single element of all of these examples. Okay, so let's do one together to start this. The first thing that we're going to try to do this for is bicarbonate. Bicarbonate is a polyatomic ion. I think it's on your list, if I'm not mistaken. It is H, CO3 with a 1- charge. Okay, and what I want to do is I want to get the oxidation number for hydrogen. I want to get the oxidation number for carbon. And I want to get the oxidation number for oxygen in this polyatomic ion. Okay? Let's go back to those rules for just a second and make sure we got the same launching point. Okay? To assign oxidation numbers, rule number 1, free elements have an oxidation number of 0. In other words, if there's an element all by itself with no charge, the oxidation number is 0. That could be diatomic as well. That could be H2, O2, N2, F2, any of the diatomic elements. Their oxidation number is 0 if it's the only element there. Rule 2, monoatomic ions have an oxidation number equal to the charge. Na1+ has an oxidation number of 1+. O2- has an oxidation number of 2-. Any element by itself with a charge, the oxidation number is the charge. Okay? Rule 3, the sum of the oxidation numbers must equal or will equal 0 if it's a neutral compound, or it'll equal the charge if it's a charged polyatomic ion. Okay? We'll deal with that in a second. And number 4, okay? If you see a fluorine, you can assume 1-. If If you see a hydrogen, you can assume 1 plus, and if you see an oxygen, you can assume 2 minus. There are a few exceptions to that, like peroxides, where oxygen is 1 minus, and hydrides, where hydrogen is 1 minus, but that's pretty rare, and AP doesn't really do that. So generally speaking, if you see hydrogen, assume 1 plus. If you see oxygen, assume 2 minus. You're generally going to have to use the hydrogen and the oxygen to figure out the other elements. Okay? Because hydrogen and oxygen are the ones that really don't change very often. Okay? So let's try this. Bicarbonate. What's the oxidation number of hydrogen? 1 plus. We're going to skip carbon because that's the one we don't know. What's the oxidation number of oxygen? That's the one that doesn't change, right? So hydrogen is always 1 plus, or almost always 1 plus. Oxygen is almost always 2 minus. And now, this is where the math comes in, okay? The overall oxidation numbers of these 3 elements must equal the charge of that polyatomic ion. I have 1 hydrogen with a 1 plus charge. I have 3 oxygens, each with a 2 minus charge. So 2 minus times 3 is -6. Plus 1 over here gets me to -5. And I want the whole darn thing to equal -1. So if I'm currently at -5 and I need to get to -1, what must the oxidation number of carbon be in the middle? 4 plus. I could write C is, but I'm just going to write 4 plus. Okay. You did this last year. Okay. You got 5 minutes. See how far you can go. See what you need to do. If you get stuck or have a question, you can turn around and ask a neighbor, or I can certainly help you. But let's just do a ton of practice so that once we start using it for real, you don't screw it up anymore. Hopefully. Sam, do you need a sheet?
I'll just print one at home, to be honest. Thanks.
You're welcome. And for those of you at home, if you'd like to just take off at this point, you're more than welcome to. Thanks for coming. Probably thank them before I tell them they can leave. There's no one here till next time.